The geometric design of stabilizers, along with other factors such as cuttings bed height and pipe speed, play a critical role in the ability to trip the BHA out of the hole. In this set of simulations, we look at variations of these factors to illustrate how they affect what is going on downhole. There are several design specifications for stabilizers, but to build the models, we focused on the following three. Taper angle. This is the angle between the leading edge of the blade and the center axis of the stabilizer. It needs to be shallow enough to be able to ride over a ledge when tripping. For these simulations, the taper angle isn't considered as a variable as the scenario is a slick hole. Wrap angle. This is the total coverage of all blades, including blade width, measured in degrees. In the image shown, each blade has 55 degrees of coverage. With 4 blades in this design, this results in 220 degrees of wrap angle. As shown on the right, a stabilizer under 360 degrees wrap angle has a line of sight through the blades. Bypass ratio. This is the stabilizer bypass area divided by the hole area. In the image, the bypass area is pointed out as the area between the bore wall and stabilizer blades. Bypass ratio is expressed as a percentage. In these simulations, the factor generally referred to as the cuttings bed height is defined as cuttings concentration, and is the cross-sectional area of the cuttings bed divided by the borehole area, expressed as a percentage. The tripping model setup is scaled down by a factor of 2.25, based on a 12¼ inch borehole, a BHA of 8 inches, and a drill pipe of 5½ inches. The fluid used in these simulations was fresh water, and the cuttings were polished stones with an approximate density of 22 pounds per gallon. The table shows the bypass ratio and wrap angle specifications of the 3 stabilizers utilized in the following simulations. Wrap angle variation. These simulations show the same bypass ratio and cuttings concentration while varying the wrap angle. With a wrap angle of 375 degrees, the cuttings accumulate through the whole bypass area, through the stabilizer blades. After decreasing the wrap angle to 180 degrees, allowing a line of sight through the blades, the cuttings don't completely fill the bypass area as they pass through the stabilizer blades. In the comparison, we can see that the 375-degree wrap angle collects far more material across the stabilizer section, which would increase the risk of pack-off. Bypass ratio variation. These simulations show the same wrap angle and cuttings concentration while varying the bypass ratio. With a bypass ratio of 40%, the cuttings flow easily through the stabilizer and accumulate slowly before the bit. When the bypass ratio is decreased to 30%, the cuttings still flow smoothly, but they take up more space between blades and accumulate much faster before the bit. In this comparison, we can see that a higher bypass ratio allows for more material to flow easily and reduces any buildup that may occur, reducing the risk of pack-off. Cuttings concentration variation. These simulations show the same wrap angle and bypass ratio while varying the cuttings concentration. With 10% cuttings concentration, the cuttings accumulate while passing through the blades, covering less than half the bypass area. While with 15%, just an extra 5%, the cuttings cover more than half of the bypass area. Both 10% and 15% are within acceptable levels, and so the stabilizer should be able to easily cope as it has done in both examples here. In this comparison, both stabilizers managed to get progress without packing off. It should be noted that the maximum tolerable cuttings concentration can also be dependent on your next operation. For example, you can tolerate higher cuttings concentration if your next run is another drilling BHA, but lower if you are running a casing string. Tripping speed variation. These simulations show the maximum wrap angle, bypass ratio, and cuttings concentration. The slower pulling speed at 0.5 feet per second easily deals with the cuttings and does not lead to much accumulation. The faster trip at 1 feet per second shows a much larger accumulation, especially in the bit body. While the simulation was still able to pull effectively, there is a noticeable difference in how cuttings flow through the blades when pulling fast compared to when pulling slow, with a faster pulling speed being more susceptible to pack-offs. Another problem with pulling fast is it gives less time to react if something goes wrong downhole, possibly exacerbating problems. In the bottom simulation, the pulling speed is high enough that the fluid velocity, along with the low viscosity of water, generates turbulent flow, which can be helpful in pack-off avoidance. This will not always be the case with drilling fluids, however. For high-angle wells, the following recommendations apply to increasing the tripping capabilities of a BHA. Taper angle should be between 30 degrees and 45 degrees, preferably closer to 30. Wrap angle should be between 270 degrees and 360 degrees, allowing for a clear line of sight between the blades. Bypass area should be greater than 35% in holes larger than 10 and 5/8 inches, and greater than 25% in holes that are smaller than 10 and 5/8 inches. Cuttings concentration must be less than the bypass ratio, but the actual maximum can be dependent on the following operation. Tripping speed should be high enough to avoid sticking or static drag, and low enough to avoid quick cuttings accumulation and allow a suitable reaction time.